All right, our next speaker is Stephanie Miller, and she'll be presenting her note on CapStones and ZebraWidgets.
Hey, my name is Stephanie, and this is work I did with Liwei Shan, Anne Rodot, and Patrick Bordish. So capacitive tangibles have been around for a moment. The one thing that I'm presenting today is how to make them stackable. We use a system of wires and a material called zebra rubber to build these stackable blocks, sliders, and dials for capacitive touchscreens. So this was a bit of a preview, but let's start at the very beginning with the history of capacitive tangibles. In 2002, when Rekimoto was looking at capacitive sensing, he already had this idea of making capacitive tangibles. He attached a thin strip of copper film to the object that transmits the user's touch towards the screen. There wasn't very much work about it at that time, but when in 2010 capacitive touch devices became mass available, there was renewed interest in the topic. For instance, CapWidgets showed how to use two markers to sense the rotation of a tangible. And at Kai last year, researchers also showed how to encode IDs, either via spatial markers or via touch frequency. And finally, at RISC last year, researchers showed how to attach tangible gain controllers to capacitive screens by using conductive rubber for the buttons and for the screen contacts. Our work is actually inspired in part by this work and in part by our own work Lumino, presented at Kai 2 years ago. All right, CapStones. So CapStones are tangible objects, as we just saw, but they are stackable. As in the previous work, they have screen connectors at the bottom and a strip of conductive material wrapped around each block, which we call user connector. As soon as the user touches the block, it becomes visible to the screen. This works because the contacts at the bottom are connected to the user's thumb with a wire. As you can see here, a single block appears to the sensing platform as 2 contact points, and when we stack a block on top, a third contact point becomes active. The one element that makes these blocks stackable are the inter-block connectors, which is a wire from the top contact to the bottom contact. So here's the trick. When we stack multiple of these blocks, the wires connect into a longer wire, which then touches the user's thumb. So the main idea again, wires connect to form a longer wire when we stack the blocks, and then one end touches the user's thumb and the other end touches the screen. So as you can see here, we can continue that concept to stack even higher. Of course, in reality, it's more complicated, so please see the paper. There are a couple of other things we can do with this. If we want to know a block's orientation, we can add this registration mark here. As you can see, the contact points are a little bit off the grid, which allows us to calculate the block's rotation. Furthermore, we can identify blocks. The trick here is that we use 2 adjacent markers. 2 active markers indicate a green block, and 1 active marker indicates a red block. And finally, we can also hand down IDs to identify the stacking order. Again, please see the paper for the details. And so here I can put that together. The system has 8 contacts. I can track the position and orientation, and you can see I can stack these blocks, and I can even identify the stacking order. So let's go one step further. Let's look at sliders and dials. We are using an interesting material here, which is called zebra rubber, that effectively transmits the user's touch towards the screen. It consists of alternating layers of conductive and non-conductive strips. Here you see a zebra slider to adjust brightness, and a stack slider to adjust brightness and contrast at the same time. So let me show you this quick video here. Here I'm putting one slider on and adjust brightness, and when I put the second slider on, I can adjust contrast. So here's how this works. Similar to a CapStone, zebra sliders have screen connectors at the bottom side and the user connector on the side. Unlike a CapStone, a slider also holds a strip of zebra rubber, and if I put my fingers on, you can see how these additional lines show up. So when we stack sliders, we can calculate the slider's position based on those lines. And for stackable dials, it's the same thing. So here you can see I use one dial to adjust brightness, and I can put a second dial on to adjust brightness and contrast at the same time. Again, for the technical drawings, please see the paper. So well, couldn't you just argue that all what we are doing is just lumino for capacitive? And I think, yes, you are kind of right. At least we were hoping it would be that straightforward. We were hoping it would be like a Boolean value. Connects to user is true, does not connect to user is false. But unfortunately, it turns out that capacitive sensing is not digital. It's analog, which makes everything a little harder. So let me explain to you the analog side of CapStones. Let's go back one step. Why did we actually need this user connector? Well, we needed it because the blocks are not sensed by themselves. The user actually has to touch them. So why is that? When the iPad thresholds capacitance into a touch and a no-touch area, the block's capacitance is actually in the no-touch area. So we asked ourselves, how can we build a CapStone that is all sensed by itself? We knew we made them from acrylic, and it didn't work. So our intuition was that we make all these walls from aluminium, and surely that would increase capacitance. It did turn out that didn't change anything. So we thought, okay, let's make the whole thing massive. That's going to work for sure. And it turned out that didn't change anything either. And I know some of you have degrees in electrical engineering, and for you all of this might be super obvious, but for us it was really interesting that primarily capacitance is neither determined by surface nor by mass. However, we finally found something that showed up. It's this long wire here. So it turns out the strongest indicator for capacitance is the length of the whole object. So we thought, oh, that's great. Now we can actually build CapStones that are sensed by themselves. We will just take this long wire, we will make it coil-shaped, and we will put it in our CapStone, and we will be fine. And it turns out others had this idea already. There's a company that makes a stylus that contains a coil to increase capacitance. So we ordered one of their pens, and we're super excited to rip it apart and to get the coil out and put it into our CapStones. But when we opened it up, we were very surprised, because the whole thing was empty. There was no coil inside. Because what really determines capacitance is the assembly from the top to the bottom, and the coil doesn't add anything to this. And in the same way, folding the wire didn't work for us either. It doesn't show up anymore. So we learned from this, capacitance is primarily determined by the length of the enclosing container. This means, if we stick with the form factor of our CapStones, we will not be able to increase their capacitance. And this has also implications on the stacking. So if we have these wires that go all the way through the blocks, the wire will at some point just be long enough to pass the threshold and will always return a true value. So we cannot sense beyond a certain stacking height. We found it very disappointing. But then it turned out we will all be fine. It's all going to work out. So here's the thing. Let's take another step back. We really wanted to make this work on a mass available consumer platform. And it turns out there's no physical need to have this threshold, because the pad certainly produces raw analog data. So in the future, we are all going to access this raw data. And I know many of you already have touchpads that give you this kind of information. So we also made our own homebrew platform for experimentation. And now we can actually build blocks that are all sensed by themselves. So here you see I put the blue block, I remove my hand, and the block will show up just without me touching it. And we will also be able to stack really high with this. So, conclusions. As we have seen, we can do a bunch of things on today's encapsulated consumer hardware. We can build these stackable blocks, sliders, and diodes. But I think the really interesting piece of hardware you want to get your hands on is a capacitive pad that gives you raw data and that allows you to set your own thresholds. So that was all I had for today, and at Hasso Plattner Institute we have an open PhD and postdoc position, so if you're interested, speak to me in the break.